Well, thank you all for coming. I'm going to hand it off to Jorge, who's going to show us the ROS robotics operating system. Guys, thank you.
All right, thank you, George. All right, well, welcome to this talk about ROS. So the name stands for Robotic Operating System, but it's not really that. It's actually a framework for developing robotics applications, and I'll explain what it is and how it works. Where's my cursor? Oh, here. All right, so here's the outline for the presentation. Hopefully the audio works well. So obviously there's the intro, which is this. Then I'll go over my background in robotics, then jump into what is ROS, history of ROS. Then I'll mention some of the more notable ROS capabilities. I'll describe some details of the ROS architecture. Then I'll jump into some coding examples with ROS in Python. And then I'll point you to some resources, and I'll then open the floor up for questions. So my background, I got my master's in mechanical engineering at UTSA. There I did my master's in robotic grasping research, where I came up with an algorithm to allow a robotic hand of any configuration, meaning any number of fingers and joints, to solve for the grasp given an arbitrary object. So those pictures are examples of how that looked like. That toy had, I forget how many different triangles. It was a very complex mesh. And so the algorithm I came up with, despite it being slow because I wrote it in MATLAB, was able to solve the grasp in about 30 seconds. This was a long time ago, so at the time that was fast. And once I finished my master's, I ended up working for Southwest Research Institute in 2011. That's when I joined. In there, I worked in a number of projects, a lot of them involving ROS, doing robotics applications in a number of industrial manufacturing type environments. And in 2021, I joined Blue River Technologies, which is a company in the Bay Area. They focus on large-scale agricultural robotics. So some of the notable ROS projects that I've worked on over the years are these. So on the top left hand, there's see the picture of that big airplane, and the blue thing right next to it is a massive robot, which at the time, talking about 2 years ago, it was the largest mobile robot in the world. It probably still is. But basically that robot was also, the software was written in ROS. And what it did is it had a laser tool with that was able to go over the plane itself to remove layers of paint. And the reason why they do that is because that's necessary for airplane inspection and maintenance. So other, I guess, classical techniques for removing paint were chemical-based, meaning you have to dump a bunch of chemical that was toxic, created all kinds of like fumes that you didn't want people around. And so that was a really terrible process. And so the laser technology with the robot was one way to overcome that challenge. Next to it is that robotic sanding project that was using a UR robot, universal robot, that had a sanding tool at the very end, and it basically went over the part. So there was a camera that took a scan of the part to figure out its geometry, and then it planned a path over the part. And then it would have the robot go with the sander and start basically making the surface smooth with the sander. And this is part of a larger painting process that a part like this goes through, right? So this was one stage where we're able to automate that particular task, which, by the way, was also really challenging for the humans to do because they had to put a lot of pressure on the sanding tool for several hours, and that caused all kinds of injuries. And so a robotic solution was, very much needed for that particular type of task. At the bottom on the left-hand side, there's that perception application. So we had this sort of vision algorithm that we wrote also in ROS to track the that box there where you see with the AR codes. So basically we were using that system to then teach a robot how to do a task. We would use the wand to move it around in space, capture the waypoints using the camera system, and then we would tell the robot to go and follow the path in order to carry out a given task, right? So it was very general purpose, very exploratory in nature, but it allowed us to demonstrate you could teach a robot without necessarily moving it through, through the actual physical points. And you could use that system to do training and all kinds of things. And autonomous navigation, this is a project that was so long ago, I barely even remember it, but I put it there because it's still a rather relevant field where we have this, what they call omnidirectional base with a robotic arm on top of it. In fact, you can see the controller, which is larger than the robot itself, which is funny. But regardless, that system, it was actually able to coordinate the movement of the base with the robotic arm in order to be able to increase its work envelope, so it could then draw that line on, I believe it was a piece of fuselage, but I don't remember. But regardless, that was the only way that the robot could actually carry out that task, since without the mobile base, it was going to be able to reach the various parts of that fuselage. So a lot of these projects, in fact, all of these that I'm showing here, were use ROS in some capacity or another. As far as my technical expertise, in addition to ROS, I'm also familiar with a number of other libraries. The Point Cloud library, which is a very popular one for doing perception type software. OpenCV, I'm sure a lot of you have heard of it. Boost, NumPy. Then there's obviously a lot of these are written in C++ mostly, but you can use C# and Python in some cases. Definitely familiar with a lot of sensors, since we have to build these systems that require perception, and we use all kinds of sensors from stereo camera pairs to light-based cameras or LiDARs. And I also got to use a number of different robots from different vendors. KUKA was a very popular one, also AUV, and Universal Robot was one that was very easy to start prototyping stuff with, and also had like this human-safe feature where like it would collide with something, it would stop. And so that kind of helped with some tasks where like the safety requirements were a little more stringent. So what is ROS? As I said before, it's a framework for developing robotics applications. It does that by basically providing capabilities and tooling used in robotics applications, right? So in any robotics applications, or at least most of them, you're going to have maybe some perception capability, potentially some motion planning capabilities and collision avoidance, maybe even some simulation. So you don't want to have to rewrite those things when those have already been invented, right? Like those things have existed for a long time, and recoding a lot of those is time you could be using for something else, and that's what ROS basically allows you to do, right? It allows you to spend more time on the novel core technology that you're inventing rather than the stuff that's already been solved. And that's what the next bullet point basically speaks about. There's, at this point, lots of support in the form of industrial drivers for either industrial robotic arms, sensors, and other kinds of peripherals. There's standardization through common interfaces, meaning, if you want to send images to your ROS system, the cameras that are ROS compliant will make that image available in the same format. So you can write your application for, for that given format. And whenever you change sensors, you don't have to rewrite your application to accept a new format, because, it's all, for the most part, it's standardized.
Is it ROS.org?
Yes. That's one of the websites. It's a open source license, Apache 2.0. I think most, at least the core of ROS is Apache 2.0. There's all kinds of ROS adjacent libraries. A lot of them do have open source licenses, but you always have to check what license they offer. But at least the core one is Apache 2.0. And there's a large community around it. You can go to ROS Answers. There's obviously GitHub. And there's also a discourse space for ROS questions. So this is sort of a high-level depiction of what ROS looks like, right? So on the left side, you have what they call plumbing. So ROS basically works by, when you have a ROS system, it's basically a number of applications that talk to each other in some way or another, right? And those interactions, the way in which these applications talk, can either manifest by way of sending messages or calling services. And so that infrastructure is what I kind of call plumbing in this, right? So you're always going to need that sort of plumbing system so that your applications can talk to one another. Yes.
Give us an idea of the kind of hardware you need to run ROS.
Well, ROS runs on Ubuntu. So, but if you're wanting to talk to, let's say, a universal arm, right? It's a type of robotic arm that you can purchase. I believe they're maybe $20,000, the cheapest one. They give you the driver or you can download it. And as long as you sent your ROS message in the established format that the driver needs it, then that message is going to make it all the way to the robot, and the robot will act on it. Does that answer your question?
Well, it tells me a lot because it's just I'm an old hardware guy.
Gotcha.
So I'm like,
Gotcha.
it's
Yes,
deeper, but I don't want to derail your
for sure.
your talk.
And yeah, that's
part of
actually a good
plumbing
point.
That's not there. Right?
Gotcha. That's a good point. So one thing I didn't mention here is that ROS runs on Ubuntu and probably a bunch of other Linux distributions. So that's really the only requirement that you need for being able to use ROS.
Yeah, well, I think both. So there's like some like hardware like standard that you have to like meet, and as long as you meet that, then you can
It's
use
more like,
ROS with it.
so the standard are like the message interfaces. So if you, let's say, if you're a robot vendor and you want to support ROS, so you write your software and then you provide an interface which is presented as a message for, let's say, accepting joint values, right? And as long as that is provided, the software that somebody else wrote that wants to control your robot will have to basically send a message in that particular format. So they both can talk the same sort of language. And that's really the only requirement there for that.
Has anybody made a toy ROS platform so that
There is a
accessible?
lot of those. There is.
So that we can play with, we can spend $500 to play with something.
Yes.
Yay. Excited about that.
So tooling, there's, in addition to the plumbing, there's basically, in a lot of your robotics applications, you're gonna, for instance, want some way of visualizing what's happening with the system, right? So ROS, for instance, provides a visualization tool called RViz, where you can see like your data, you can see three-dimensional point clouds, you can see images, you can even see virtual robots sort of acting on joint commands if that's what you're doing. And you can also do things such as you can see what the programs are printing on the console. So ROS has tools for those kinds of things. On top of that, you have capabilities. So for instance, if you want to do motion planning for a robot after you observe some object that you want to go pick up, rather than having to write the motion planning algorithm, you can look to see if there are capabilities that already provide that for you, right? So you can use some capabilities out of the box. For instance, for motion planning, there's Move It. For perception, there's the point cloud library, and there's capabilities like that for things that are very commonly used in robotics applications. And the ecosystem is, what I mentioned before, all of the forums and GitHub and these various places on the internet where you can go ask questions and get support for, for when you're developing robotics applications using ROS. So the history of ROS, is belief. All right, echo is gone. Okay, so it started out as a project at Stanford where two engineers, whose names I can't pronounce too well, so I won't say them, but you can read them there. They took notice of a trend that was rather detrimental for robotics itself, right? In that a lot of the time spent on doing anything with robotics was spent on reinventing the wheel. So you always had to write the same inverse kinematics, you had to write collision detection, you had to write maybe some form of visualization, and you were not actually contributing anything new to the field of robotics in doing that. And so that's, that goes to show, like, this chart here shows you like all of the red that was basically spent on stuff that was not advancing the field, right? And so in response to that, they decided, well, let's create a common framework for robotics. That way people are investing more on the green stuff. And so that's what motivated ROS in the first place. And so kind of formally, ROS started or was led initially by Willow Garage in 2008. And in 2014, I believe the company got disbanded, and the ROS maintenance was passed to OSRF. And in around 2015, after ROS have been around for a while, there was a lot of people who had come to use it, and obviously, they could take advantage of it, but also understand the all of the different limitations that it had. And as a result, kind of the ROS2 project started, which was basically going to address all of the different problems and limitations that ROS or the first ROS had, right? And in 2015, ROS2 was released and is the current ROS version that exists at the moment. And you can see on the right-hand side all of the different releases of ROS. Actually, this is a little outdated because I believe there's a couple more after the 2023 release. But if you go to the website, you'll probably see the more updated, up-to-date list.
The license agreement is what? What kind of license agreement is it? GNU? Is it Apache?
It's Apache. It's not in this slide. I believe there was in a few slides back.
Sorry, old man.
No worries. So applications built with ROS, I showed a few earlier, but there's a lot more that have been built. There's robotic applications built with ROS for agriculture, like plant picking and stuff of that sort. Obviously, we've all seen some warehousing robotics stuff, right? There's probably one of the more mainstream type robotic applications. There's a lot of robotics applications with ROS for bin picking. The one on the bottom left is one that I actually participated on for a little while. It was a fastener insertion. So they were working. They have robots inside the hull of an airplane. They were inserting fasteners inside for assembly purposes. There's been a lot of ROS robotic applications for painting, car painting, and there's all kinds of academic research where ROS is heavily used because, like I said, it allows you to get going very quickly. So this is more on ROS capabilities. So you can see the pictures around like the boxes there, but perception, there's a ton of stuff for using perception with ROS out of the box. There are algorithms where you can do tabletop detection. So you basically run it and it'll kind of remove all of the points from the table and just retain everything that's on top of it. So that way you can do further processing if necessary. There's all kinds of visualization tools. There's simulation. The main simulator that comes with ROS is called Gazebo, where you can represent all kinds of things, including robot dynamics, and you can represent sensors, or you can actually simulate sensors, which is a very useful tool. And there's all kinds of capabilities that are tightly integrated with ROS. And there's data logging as well, machine learning. It's not all that built into ROS, but it really doesn't have to because the machine learning is sort of its own separate thing. There's a lot of effort that has been invested in motion planning, especially for robotic arms. The main library there for that is called MoveIt. So MoveIt has been around for quite some time, and it's like I said, a very advanced motion planning library for that particular type of capability.
So is this something that we can use Python to coordinate all these services? Is that the vision?
So a lot of this is actually available in C++. Right. Some of these have been ported to Python. Most of the time it's usually to Python bindings.
Right.
But
it doesn't need to be in Python.
Right.
But easy access.
Yes. So most of these are open source. Like you can find a lot of these either most of the time on GitHub. So you can find, for instance, MoveIt is a GitHub library, and you can clone it into your repository, into your application, and use it. So the list is actually larger than this, but all of these robots and sensors are fully supported in ROS, right? So you can, if you have one of these robots, you most likely be able to use it with ROS. Same for the sensors. So if you have a LiDAR, like you plug it into your ROS system, and then you can even visualize the 3D point cloud with RViz.
It's like it's being used in drones too.
Yes. Yep. So ROS and AI. So this is something that, like I said, it's integration with ROS depends on the application a lot of times, but these are projects that I'm familiar with that I've ran into. One is this ROS object detection, which uses some learning algorithm provided by NVIDIA, I believe, to detect objects from an image. And then, they provide a way to make that result available within your ROS application. And then on the right-hand side, this is a pose estimation algorithm also using machine learning, where it takes a picture or several pictures and then it comes up with the pose and the bounding box for the object. So those are things you.
We can build robots with, say, NVIDIA Jetson embedded systems.
Right.
And have them doing this stuff
Right.
in the leaf,
Yes.
out in the robot itself.
Yep.
Very cool. Very cool. Thank you for sharing.
Yep. And so this other was one I ran into. Let's see, the video is not playing.
I got access to a video.
Oh yeah.
It's okay.
Then okay. Anyway, this was just a cool example of somebody who had integrated some ChatGPT style interface on the command line. So like, let's say if you wanted to do some introspection of your ROS system, you could tell the interface, you can ask a question as you would with ChatGPT, right? If you wanted to ask, hey, how many messages am I getting on this topic per minute or so, then you can ask that question and it would tell you either how to run the command or it would actually run the command for you, give you that result. So it's an interesting project, but at the moment this is more like a help tool rather than something you would use to develop your code. Okay, so this is a very simple depiction of what a ROS application looks like, right? So in ROS, you have what is called a ROS nodes. And a node is an application basically that has, ROS code embedded in it. And that ROS part is what allows it to talk to other nodes. And nodes interact in a bunch of ways. One of those, or the main way usually, is by topic. So there is usually, in a topic interaction, there is a publisher and a subscriber, right? So the publisher sends out messages through a topic, and all of these subscribers that are listening on that topic will get that message. So this is a very typical type of interaction in all kinds of applications. ROS basically follows that same model.
Are there real-time guarantees on these messages?
Not on these. There's also services, which is probably something that a lot of people are familiar with, but in a service interaction, there is a request that is sent by a client, and as long as there's a server that is listening for that request, then the server will act on the request, whatever that is, and then send back a response, right? So this is different than the topic in that it's a one-to-one interaction, and the transaction goes back and forth between the client and the server, as opposed to the topic where it's usually a one-directional exchange. In ROS, there's full support, at least for the core libraries. There's full support for C++ and Python, and I believe there's some experimental support for Rust, which I'm not familiar with. I actually haven't used it, but I've kind of read a little bit on that. So this is a more sort of detailed description of what the ROS architecture looks like. So at its core, like ROS, or the communication in ROS, is done through a DDS, which stands for Data Distribution Service. And then on top of that, you have what is called the ROS middleware, which is basically wrappers around the DDS applications. And then even higher up than that, you have what is called the ROS client library, which is what if you write a ROS application, you'll be using code in the ROS client library to create publishers, subscribers, services, in order to be able to allow your application to interact with the rest of your ROS system. And at the top of that, there's the user application, which is your code, right? Which, as I mentioned, will use the ROS client library to build the ROS application itself. So here's an example of how you would write a a publisher in ROS in Python. So you always, obviously, you have to have your main and then your libraries. In this case, that at the very top, you have the ROS or the RCL-Py, which is the Python ROS library. So you call that, and you always call the init function and pass the arguments that were passed into the main. After that, you always have to create a node. So this is mandatory for every ROS application. You initialize with the init call and then the create node. So once you have that, then you can start building ROS artifacts. In this case, we're creating a publisher through the node by saying, we're going to publish this string message on this topic, which creatively called topic. And the 10 is just basically a sort of an internal buffer that it maintains, and that's application specific. So don't worry about it too much. Anyway, once you create the publisher, then you create a message, and in the while loop that's below it, you go ahead and start publishing the message itself, right? So since we're publishing a string, we're modifying the string on each iteration by incrementing the integer. And then basically every new message that you get or that you publish will say hello world and whatever the integer count is. But obviously a very simple example, but it conveys what you need to do in order to be able to publish a message.
And you can tell it's just really a C++ developer by this, where you don't have the F string, you have the %S, and you define your message as a string.
Yes, very good catch.
Security problem,
Is it?
almost all.
They use F strings now.
Template strings, that's Python.
Cool. Well, so
yeah, don't worry.
No, we're giving you shit, that's all right.
yeah, that's cool. I mean,
The fact that there are security problems on the interior of a robot operating system is to be expected.
well, it should be guarded by a firewall, right?
You couldn't have MurderBot be a story on Apple TV in a few days
Well-
and have security problems, right?
I will say it's all because of the string.
You're on safe ground,
Exactly.
very safe.
Okay, so since we're publishing a message in the previous example, then now we need a listener, right? So this is the way you write a listener. First, you start with your main as usual, and as I mentioned, you need a ROS node, and then you have to call the init function. And after that, instead of creating a publisher, as we did in the previous example, we create a subscriber. So that's a subscription line there. And basically, the way you call this function is very similar to the publisher, but instead of passing just the message type and the topic, we actually pass it a callback. A callback is a function which will be used to receive the message. And so that chatter callback, if you look at how it is defined, what it does is it has an argument to receive the message. And in this case, we're just printing the message to the console. But for a more sort of realistic application, you would do something a lot more complex than just printing the console. Anyway, once you set your subscription or your subscriber in this case, what you do is you spin the node. So that ROS or RCL-Py, that spin once, basically is what it's doing is calling a bunch of internal ROS code to trigger the callbacks once a message is received. And that's how your chatter callback function is able to process the message. And once you're done, let's say you Control-C the application, then it'll go into the next line after the while loop where the node is destroyed and then the application shuts down.
Speaking of this, the Python group, has anybody wrapped all that stuff in asynchronous IO, because those are IO calls, basically IO calls. Whether it's talking to hardware or not, it's outside process communication.
Mhm.
And so that would be a classic mapping into the async IO handler. Because you're just talking about spinning up, talking to
Right.
underlying thread management tools that then talk to, go down your stack and talk to the DDS and then bring back messages. And Python has mechanisms for hiding all of that so that we don't get our hands dirty.
Yeah, that's basically what this does too, right? Like it kind of hides all of those details for you. You could definitely delve deeper into this. You can provide your own execution queue method if you needed to do something more specific. But most of the time, you don't really want to deal with that. You know, it doesn't, you know, it depends on the application that you're building, right? So the other example that we're going to go over is the server and client interaction. And in this case, what we want to do is we want to call a server with a request, right? And the way you do that is very similar to the publisher subscriber model. But in this case, for the server, you create your server by providing a callback, and the callback has two arguments, one being the request and one the response, right? So once the service call comes into the server, you get the request with the data that you're supposed to operate with, and then you, through some calculation that is application specific, you'll provide a result which you then will put back into the response, and that is what gets returned to the client. And so on the client side, you really don't have to do much other than building up the request structure, which we're doing on that sent request. As you can see, the request is basically just setting these two fields, A and B, and then it's making the call async, which is what is when you send the request to the server, and then you wait until the server has time to process it and return a result, which is what you get in the future result function or line there. And that's basically it for the Python examples. These are some resources you can go to. As I mentioned, there's a ton on GitHub. There's a lot of demo code you can look into, and you know, there's even a website where you can go take ROS training at some cost, of course, but I believe there's some free lessons you can actually also look into. And yeah, so these are all of the resources at your disposal, or at least some of them. There's probably a lot more that I have covered here. Anyway, with that, do you have any questions?
Are these controlled with ROS?
No.
No.
He brought them here. So, yeah.
Okay. Joe says like, bring the robots. Okay, I'm going.
I don't really have any experience with robotics, this might be a dumb question, but is the assumption in the ROS setup that there's like a PC or a laptop or something that's actually Python? Yeah.
Most of the time, that is how that is set up.
Okay, so it's like a single PC,
Yeah.
there's all these different devices.
Right.
And you mentioned nodes and then using different bits of Python code. How do those map to, robots?
So for instance, yeah, let's say you have your laptop that's running, your perception algorithm and also motion planning. And once you do those steps, you have a, command for the robot, right? At the end of that. So then your robot is either on your network or directly plugged into an Ethernet cable. And the robot itself is running software that provides an interface to receive the command, the ROS command that is being sent by your ROS software. So like usually a robot has its own robot controller, meaning its own computer, right? And that will be running processes. One of those being a ROS driver, which is basically in a lot of cases has a ROS subscriber. And so the ROS subscriber is waiting for a trajectory message, for example. And once it gets a trajectory message from one of the nodes in your running your laptop, then it will then consume that and execute it internally. In the case of a camera, cameras also provide their own drivers. So there's software running on the camera, or sometimes in your laptop, right? Just talking to the hardware, and it's pulling out the images, and then converting those images into, let's say, a ROS image message type, and then it's publishing that. And maybe you have a perception node that needs to do something with those images, so it subscribes to a image topic to receive the messages coming from the driver that is, reading images from the camera.
Is your partner using ROS to configure that camera to send out those images regularly, or?
It depends on the camera. A lot of times, like the more ROS compliant ones don't really have you do much other than plugging it in and installing the ROS side.
Was ready to send out a
Right.
survey, which is,
Yep.
subscribe.
Yes. Yep. Yes.
I have a question for you. So you've been in the robotics field for a while. There's been what it looks like a lot of advancements recently in the last year.
Yeah.
But how much of that is it feels like a lot of the problems in automating and manufacturing it's always been kind of doable, but we didn't want to put money into it maybe. What are your thoughts on that versus does all this new, AI really enable us to make robotics for certain tasks cheaper? Does that make sense? For manufacturing, some of the things you showed, you the sanding one, you said they had to do that because people were getting injured. That was a task that was automated away.
Yeah.
As we see more things get automated away, do you see the AI being a big mover of those things, or do you think that we already could have done them? But maybe they're easier, maybe they're cheaper now.
Definitely in the perception space, right? I think that's where it's making more of an impact.
Clearly in your grasping issue, I mean, you said you did your stuff in MATLAB.
Mhm.
I mean, if I fired up a NVIDIA Jetson card, I mean, it will screen through that MATLAB code. Just wicked fast, but it's all matrix multiplications.
Yeah.
Right. So in other words, what used to take you 30 seconds will probably now in the millisecond range on some of these low.
Yeah, as far as the processing power, of course, things have gotten significantly faster and more efficient.
all sorts of things can happen now.
Right.
Yeah,
Very, very
can
fast.
be on a big
Right.
extent. So those two arms right there. So one of the the reason I got so excited about robotics recently is because the industrial robotics, I think it pretty much solve most of the problems. It's very precise, right? But they have something that they have to go from point A to point B, repeat a million times over, right? So what's exciting about this, for example, I can train those robots. I can show it they have to show you right now. They have to show you quite a few times, 50 times, to show how to pick a cup from one place to another in talk place and move it from here to there. But then I can move the cup around, and then it still figures out where to go and pick it up. So I think that's kind of what's the advancement. I don't know. Are there anything like that?
So it's definitely making a huge impact on tasks where there's
It's more generalized.
there's a lot of unstructured.
Yeah,
It's an unstructured problem that doesn't require a great deal of precision.
Yeah.
Right. So in those tasks, such as bin picking, for example, the new sort of AI technologies that have appeared in recent years, those are able to solve those problems very well, because what was there before were classical algorithms where whenever a new element was introduced, then you had to make adjustments to that, but as opposed to now, you just kind of train the network, and for the most part, you can just run with that and then command the robot to do the bin picking if that's what you're doing, right? But if you have something that requires a great deal of precision, not to mention, you also have to account for the force, like the physical interaction with the object that you're in contact with. In that, I still haven't seen much of a major breakthrough. For instance, if you're doing a very precise welding task, then I haven't seen anything AI related that can tackle that better than, what more traditional approaches have done.
I've seen, so on the other side of the fence, I've seen examples where now with this very simple robot arms, you can do towel sort of folding. It might not seem like a big deal, but there's a lot of hotels and they have people that just they fold a bunch of towels every day. So they show they were able to fold 800 towels with no problems or something like that. So it's more as I said, when it comes to the very precise thing, I think we still need more the traditional robotics or unstructured things like holding a towel. That's when the new AI comes in and brings more advantage in that area. So.
So follow-up question: When do I get a robot that folds my laundry? You think next year?
Next year. Yeah.
126. You want to put bucks on?
Which I'm working on. I made a deal with my wife. I'm gonna make a robot that's gonna unload the dishwasher and put stuff on the shelf. So So I'm learning everything I can as far as the AI, using those two things, and then I'm gonna expand from there. Like I'm building, like using CAD to build bigger arms, so I can, but I still use the software, the AI software that I'm gonna use it for these to connect software from there. But yeah, maybe a year from now I can, if you can ask me.
But yeah, so I think the biggest impact is in the perception space. Right.
You had mentioned that there are some toy versions. I saw on your slide, like Lego of NXT, stuff like that. Would you say that's maybe?
I believe there are more like ROS dedicated platforms you could probably buy. The NXT stuff, I haven't seen too much of that in a while.
We used to do that in high school. I didn't
Yeah.
use ROS, just whatever, did it Java,
Mhm.
whatever packages we used there. Talk to it.
But if somebody was wanting to, I guess, learn ROS, what would be the cheaper $500 or under kind of hardware?
It's been a while since I looked into that. I want to say the Turtle Bot. I don't know if those are still around. You might still be able to buy a Turtle Bot, but basically there are these units that are, ROS specific. We have all of the sensors and computing units.
Can you connect it to a DJI drone?
DJI drone.
Do you know the DJI drones?
I'm not familiar with those.
I don't know those things.
I know those, yeah.
Yeah, they're like a very popular consumer drone. They have a camera on them. I wouldn't want to like control it with ROS, but it would be interesting.
So if you Google ROS 2 robot toy, there's a whole bunch of things that pop up.
Probably would love it.
Okay. Like a robot car at $439, all sorts of stuff.
Yep.
Robot dogs, $840. So
You mentioned simulation as part of that. Like, how does that work? How realistic is it to set up a simulation and run it, repeatedly with machine learning, word functions or something, and try to figure out the right thing?
So the simulation is, is going to try and mimic parts of the real world to a certain degree, right? How realistic that is sort of up to your application. If you have a model that is very detailed and, you have the proper dynamic parameters and all of that, which is not easy to build. But if you can do that, then at least the one that I know, which is Gazebo, can do a fairly decent job. Has all of these internal models for, various dynamic objects. So you can get a rather realistic simulation. As far as ROS is concerned, what it does when it comes to this simulation software, a lot of the data that is generated within the simulator gets published as messages, ROS messages that you can then, listen to. So for instance, if you have a virtual camera inside your simulator, you can subscribe to that camera topic and actually see the image in your ROS system, right? And then you can have maybe some perception application that takes that image and does something with it. And it should work the same for the most part if you were to have a real camera instead, right? So you use it as some sort of replacement for the physical things that you maybe don't have in the moment, but you will have eventually, right? And you can start to build your application using the simulator, providing the data that would be generated by an actual physical system.
Automated testing.
Yep, you can do that too. Yep.
Is there a question in the chat? Whoever that thing was.
I think it was somebody posting a link to a meetup.
If there's any other questions you can ask Jorge after, we'll be here, but
Hey, Jorge, I have that question.
Yes.
Hey, thanks for this background. I've been tinkering very little with ROS. But my question is related to how do you see it in the in this new experimental direction where neural networks are more end-to-end, and there is less of a concept of particular narrow skill like motion planning or perception or grabbing an object. It's more like visuals or audio in and actions out. Do you know if there is an ongoing or separate branch of ROS that optimizes for that sort of direction, or you think it'll be, you don't think it'll fit in that type of projects? I've been wondering why I don't see ROS much in the cutting phase with robots, for example, as a project.
So your question goes along the lines of ROS adoption?
Okay, so do you see ROS playing a role in how, when it comes to deploying models that are end-to-end, robotics models that are end-to-end?
I don't see how it, so ROS wouldn't be in the way, or in the way of that, right? That's sort of its own separate discipline. ROS providing a lot of tooling for you to build your robotics application, and sort of the model deployment that can still happen, and it can, you know, be done in its own custom way that best suits the application at hand. At the end of the day, ROS just gives you a bunch of like tools and capabilities to integrate that into a larger system, if that makes sense. But as far as model deployment, at least that is something I see as outside of the scope of ROS, at least for the time being. It may become eventually something that it tackles, but it's not necessarily within its scope.
That's just a service in the ROS
Right.
framework.
It could be a service. Right?
Yeah,
It could be something that you integrate into an existing ROS application.
That makes sense. Yeah, I just see it as more of a hierarchical architecture of deterministic modules that work together, and each of them is well tested for a specific task. You know, from coordination to more particular skills, as you explained, and where these end-to-end models are supposed to be direct sensors in, and on the other side are outputs to arms or whatever is the acting.
Yeah,
No.
so you could think of ROS as like a Lego set, right?
Mhm.
And you know, you can either, you know, use pieces that are there or ignore them altogether, and you know, maybe build your own 3D print your own Lego piece if that's what you're, you know, what you want to do, because it fits within what your goal is, right? So so if you're talking about applications that are deterministic, there are a lot of out-of-the-box capabilities that are deterministic, but you don't have to use those if you have something that is more suited for whatever problem you're trying to solve.
Okay, appreciate it. I'll do some more digging to understand it.
Hey, I have a question here.
Yep.
So the question regarding adoption, right? Do you see companies, you know, moving from non-ROS platform to, you know, ROS, you know, because it's open source, it's more, you know.
Yeah, so on that, to be honest, I've seen that larger companies are more wary of using ROS because of that concern, right? And also they have the budget to do basically build everything from the ground up to suit their needs, right? But mid-sized to smaller companies are more likely to use ROS because it saves them a ton of money, and not having to build the infrastructure, not having to build a simulator, not having to build their own visualization tooling. So that's the trend that I've observed, right? So every now and then I'll see companies that start with ROS to do a prototype, and once they're happy enough with the prototype, they'll start optimizing, and they realize, well, you know, ROS may not be exactly what we need, so they'll rewrite huge chunks of the code to do exactly the same things, but maybe in a way that is more specific to their needs.
So that's a really huge investment for someone to do.
Yeah.
So they must feel that something that ROS is doing is wrong, or in terms of performance or costs. So, but it sounds like what you have is a very thin, like you sit on top of a Linux, it almost looks like you could run on very low end stuff. risk Raspberry Pis,
Right.
and probably risk-based systems, et cetera.
Right.
And so services can be run very, very thinly and cheaply. You have a little bit of networking. So where is the big expense that that the system imposes? Because it looks like a relatively straightforward, basically robot system bus and a direct point-to-point service bus.
Yep.
Right, with good high performance communication, probably not a lot of probably say everything's little Indian, so fundamentally you don't even have byte order issues, et cetera. I mean, it's only when you hit a real network you have to worry about network Indian. So where does someone?
So one of the cases that I've observed personally is so ROS has its own storage system, right? They call it ROS bags, but you can basically collect messages and store them in these, buckets called ROS
Logging system.
right? So the one instance that I saw where that was that motivated not using ROS, or at least moving away from it, was that they wanted their own custom storage system, and whatever ROS offered didn't meet the requirements for that. And I'm not necessarily I'm not all that knowledgeable in the details of what those requirements were, but ROS did not meet those, and so they decided, well, we're just going to invest all of this effort into re-architecting or architecting our own, our own ROS system, so to speak, right? Our own home thing to tackle that problem.
So you have to imagine medical applications come in with all sorts of stupid requirements
Yeah.
that ROS might not be.
Right.
I can imagine military applications coming in, but they're probably wrong because ROS has real-time performance requirements that sort of like make systems.
So the real time is one thing that is actually, even though that was one of the main motivations of ROS 2 when it was coming out, was something that's not fully implemented, and that's another reason for some companies to build their own message passing system to kind of build the real time part of it in a way that meets their requirements, right? So an application has these very tight time windows, and for a lot of those, maybe that ROS doesn't meet those. And so I've seen companies that, or at least one company, that basically moved away from ROS in order to build their own thing because they have, like I said, these very strict time windows in which a message has to be sent and received and processed in a single cycle. Otherwise, the task was not going to be able to get accomplished in a satisfactory manner. And so, but these are like very specific cases. And like I said, a lot of times comes down to the amount of resources that are available to a company that makes them take that decision, right?
I mean, there's so many variables.
Right.
Right. A modest-sized industrial robot has probably 4 or 5 processors in it, each of which is a ROS node.
Yep.
And a communication network between them all.
Mm-hmm.
So, and there's contention issues, et cetera. So I can imagine a bunch of people convincing themselves that they need to have something with more control.
Right.
Versus just, let's put a faster processor in each of these
Right.
nodes.
And there's also that, right? Like the control work that you mentioned is another reason for motivating someone to create their own library, because if you want to contribute something to ROS, like a change, then it has to go through a review process. We've all done pull requests, and maybe that's not what they want for ROS, and that can be frustrating at times, and that motivates some companies to let's just build their own thing, and we don't have to deal with that.
They've got an infinite budget, don't they?
Yeah, exactly. I mean, like I said, large companies do have that luxury.
And what you've just shown is probably a couple 100,000 lines of code. That's expensive to have done.
Right.
Really expensive.
Yep.
Well, thank you, Jorge, for your presentation. Let's cut the recording. We've been here for a little bit. We're going to head down a punch bowl.